magnetic fields, task number 7. All right, so it's the same problem as the problem that we did before, except it's in numeric form. Proton is being shot out of a capacitor into a constant magnetic field region. It's going to go into circular motion. And the only thing we need to figure out is its radius of that circular motion. So inside the capacitor, what do we have? We've got a constant electric field region, so there's a separation distance. So there's going to be a voltage difference. This is what's going to be driving the protons into the hole in the negatively charged region. All right, so let's get the numbers in. The problem that you had to do was non-numeric, so I'm going to skip the numbers. We got the mass of the proton, we got the charge of the proton. So what do we know? This is circular motion, so we know that there's centripetal force. In this case, is the magnetic force. Here's the centripetal force formula. Here's the magnetic force formula. Angle is going to be 90 degrees between the velocity vector and the magnetic field. So sine of 90 is 1. We do a back substitution for those equations. Solve for R. All right, so get rid of the like terms. Notice that the speed is the only thing we don't know in this case. So we got terms for Q, B, and M. So proton is going to gain speed within the capacitor. We know that the strength of the electric field is constant inside the capacitor. Electrostatic force is a conservative force. And conservative force acting on the charge is going to reduce its potential energy and increase its kinetic energy. So which means that the potential energy is going to turn into kinetic energy. Initial speed is 0. All right, so potential energy is expressed in terms of potential difference. Change in potential energy is going to be expressed in terms of potential difference as well as the charge. You can ignore the negative sign because you're looking at the potential difference. Negative sign depends on the reference point, so you can just change your reference point so in order to actually get rid of it. Initial speed is 0. On the left, you got kinetic energy. On the right, you got your change of potential energy. Solve for V. All right, so now that we get an expression for V, substitute into the expression for R, the radius. All right, and notice that we got a bunch of like terms inside the square root as well as the outside. So get rid of the square root by squaring both sides first. And then take the square root of both sides. Square both sides first. Get rid of the like terms. And then square root both sides. That's it. All right, so the final expression has everything given. We know the charge of a proton. We know the mass of a proton. We know the potential difference. We also know the strength of the magnetic field. Extra credit problem. So what we have, compute the value of the magnetic dipole moment for the hydrogen atom. Mass is given, the charge is given. All right, so let's list everything first. All right, so this is the Bohr hydrogen atom. Electrostatic constant, so the mass of the electron, the charge of the electron, the size of the hydrogen atom. So figure out the magnetic dipole moment. Here's the formula for the magnetic dipole moment, number of turns, area of the cross-sectional area of the atom, and the current within the atom. And it's going to be 1 because we have only 1 electron. So area is the area of a circle because the electron is going to be undergoing circular motion. Now we need an expression for the current. Current is the net charge per second. All right, so we can express it in terms of the period of this motion. Capital T is going to be the period, so the time it takes for the electron to make a single circle at constant speed, single cycle. All right, so speed is going to be circumference over period. Circumference is 2 pi r. Right, so period is period. Notice that this expression is going to be 1 over time, so 1 over the period will match that expression. So we can do a back substitution. Our current is going to look like that. So you have the charge moving at the speed through the circumference of the circle. All right, so we do a back substitution to the dipole formula, magnetic dipole formula. All right, so we got some cancellations. And all right, so that's what the final equation looks like. Except we need to figure out the speed to get a better idea. So we have an expression for Q, we have an expression for R. All right, we'll get the speed, knowing full well that this is circular motion. And the centripetal force is the same as the electrostatic force. Get rid of the like terms. Solve for V. Q1, Q2 This is the charge of the proton, the electron, take the absolute value. So it's going to give you E squared, both of them are unit charges. And then get rid of the square of the V. And then do a back substitution into the dipole formula. All right, E is the same as Q, so I made the adjustments. All right, we got the like terms, we got R here, we got R there. All right, so there are further cancellations. Get rid of the square root by square on both sides, and then take the square root of both sides after the cancellations. And this is the final formula. And that's it.